Hey there, science fans! Today we're diving into the fascinating world of acids. You encounter them every day, from the citric acid in your orange juice to the acetic acid in your vinegar bottle. But did you know that there's a whole system for naming these tangy compounds? Acids are like the rock stars of the chemistry world. They're full of energy and ready to react. We can divide them into two main groups: binary acids and oxyacids. It sounds complicated, but stick with me. Binary acids are the simpler ones, made up of just hydrogen and one other element, often a nonmetal. Oxyacids like to spice things up with an extra oxygen atom in the mix. Ready to unlock the secrets of acid names? Let's get started. Let's start with binary acids, the simpler members of the acid family. Remember, these guys are made up of hydrogen and one other element, usually a nonmetal. Think of it like a duet. Hydrogen takes the lead, and the other element harmonizes. Naming these acids is like learning a secret code. When we talk about the pure compound, we use a system similar to naming ionic compounds, even though they share electrons like the best of friends. We start with the name of the nonmetal, but we add an ID ending. Then, we add hydrogen at the beginning, like we're introducing the lead singer of our duet. For example, let's take hydrogen and chlorine. When they team up as a pure compound, we call it hydrogen chloride. It's like saying, "Ladies and gentlemen, please welcome to the stage hydrogen chloride." Now, things get even more interesting when our binary acid duo takes the stage in a water solution. Imagine hydrogen and chlorine atoms as performers, ready to dazzle the audience with their chemistry. Water is like the ultimate hype crowd for acids, causing them to ionize or break apart into charged particles called ions. This ionization is crucial because it allows the acids to exhibit their unique properties, making them more reactive and dynamic. This is where the hydro prefix and IC suffix step into the spotlight. These naming conventions are not just for show. They help chemists identify the specific type of acid and its behavior in a solution. We use this special naming convention to show that the acid is now performing its act in the water solution. It's like giving the acid a new identity that reflects its enhanced capabilities in water. Let's revisit our friends hydrogen and chlorine. These two elements are quite the dynamic duo, especially when they interact with water. When hydrogen chloride gets dissolved in water, it forms hydrochloric acid. This transformation is not just a simple change, it's a complete makeover that allows the acid to showcase its full potential. See the pattern? We swapped the ID ending with IC and added the hydro prefix. This systematic approach helps in easily identifying and understanding the nature of the acid. It's like giving our duet a cool stage name for their electrifying performance. This new name signifies their readiness to engage in chemical reactions with other substances in the solution. Other examples of this transformation include hydrogen fluoride becoming hydrofluoric acid in solution. This change is significant because hydrofluoric acid has unique properties that are different from its gaseous form, and hydrogen sulfide turning into hydrosulfuric acid. This transformation highlights the versatility of binary acids and their ability to adapt to different environments. It's all about adapting their names to match their new, dynamic state in water. This adaptation is essential for chemists to accurately describe and predict the behavior of these acids in various chemical reactions. Understanding these naming conventions and transformations is crucial for anyone studying chemistry. It provides a foundation for exploring more complex chemical reactions and interactions. So next time you see a binary acid in a water solution, remember the fascinating journey it undergoes. From a simple molecule to a powerful acid, it's a transformation worth appreciating. And there you have it, the unmasking of binary acids in solution, a captivating performance that showcases the beauty and complexity of chemistry. Section 4. Diving into the world of oxyacids. Ready to level up? Let's dive into the world of oxyacids, where things get a bit more complex, but don't worry, we'll break it down together. Oxyacids are fascinating compounds that play a crucial role in various chemical reactions and processes. Understanding them can open up a whole new dimension in your chemistry knowledge. Oxyacids are like the larger musical ensembles of the acid world. They are more intricate than simple acids, and their structure and naming conventions can seem daunting at first. But just like learning a new piece of music, once you get the hang of it, it becomes second nature. They have hydrogen, oxygen, and another element, often a nonmetal, joining the band. This combination creates a unique structure that defines the properties and behavior of the oxyacid. The nonmetal element can vary, leading to a wide variety of oxyacids with different characteristics. Naming oxyacids is all about understanding the ITE and ate suffixes. These suffixes are derived from the names of the oxyanions, which are the negatively charged ions that contain oxygen. The suffixes help us identify the specific type of oxyacid we are dealing with. These suffixes are key to unlocking the secrets of the oxyanion, which is the negatively charged part of the acid molecule that contains the oxygen. The oxyanion structure and composition determine the properties of the oxyacid, including its reactivity and acidity. Think of it like the rhythm section of our acid band. Just as the rhythm section provides the foundation for a musical piece, the oxyanion forms the core of the oxyacid structure. Understanding this core helps us predict how the oxyacid will behave in different chemical reactions. If the oxyanion's name ends in IT, we use the OUS suffix for the acid. This naming convention helps us quickly identify the type of oxyacid and its corresponding oxyanion. For example, if we see an acid with the OUS suffix, we know it contains an oxyanion with the IT suffix. If it ends in ate, we use the IC suffix. This is another naming convention that helps us identify the type of oxyacid. The IC suffix indicates that the oxyacid contains an oxyanion with the ate suffix, which often means it has a higher oxidation state compared to the IT oxyanion. It's like choosing the right costume for our oxyacid based on its rhythmic style. Just as a musician selects the appropriate attire for a performance, we use the correct suffix to name the oxyacid based on its oxyanion. This helps us communicate effectively about the specific type of oxyacid we are discussing. For example, HNO2 contains the nitrite oxyanion, NO2. The nitrite oxyanion has a lower oxidation state compared to the nitrate oxyanion, which affects the properties of the acid. Understanding these differences is crucial for predicting how the acid will react in various chemical processes. So, its name is nitrous acid. The EOUS suffix indicates that it contains the nitrite oxyanion, helping us quickly identify its composition and properties. This naming convention is a useful tool for chemists to communicate about different types of oxyacids. On the other hand, HNO3 has the nitrate oxyanion, NO3, so we call it nitric acid. The nitrate oxyanion has a higher oxidation state compared to the nitrite oxyanion, which gives nitric acid different properties and reactivity. This distinction is important for understanding how different oxyacids behave in chemical reactions. See how the suffixes match up? By understanding the naming conventions and the structure of oxyacids, we can better predict their behavior and reactivity. This knowledge is essential for anyone studying chemistry, as it provides a foundation for understanding more complex chemical processes and reactions. Section 5. Naming oxyacids, a suffix symphony. Let's explore more of those suffix symphonies in action with some other oxyacids. Take sulfuric acid, for example. Its chemical formula is H2SO4. Notice the sulfate in there? That tells us it contains the sulfate oxyanion, SO42. Because sulfate ends in ate, we use the IC suffix for the acid name, making it sulfuric acid. It's like sulfuric acid is dressed in a grand tuxedo for its performance. Now let's look at sulfurous acid, which has the formula H2SO3. See how it contains the sulfite oxyanion, SO32. Since sulfite ends in IT, we use the US suffix, giving us sulfurous acid. It's like sulfurous acid is wearing a more casual outfit for a relaxed jam session. Remember, the key to naming oxyacids is to pay attention to the oxyanion suffix. Once you've got that down, you can name these acids like a pro. Section 6. Don't forget the famous faces. While we're busy naming acids, let's not forget about some of the famous faces in the covalent compound world. These are compounds that share electrons, just like our acids, but they don't always follow the same naming rules. One such celebrity is methane, CH4, the main component of natural gas. It's like the superstar of the energy world. Then there's ammonia, NH3, a common ingredient in fertilizers and cleaning products. And of course, we can't forget about water, H2O, the essential molecule for life on Earth. These compounds have common names that we use every day, even though they don't strictly follow the acid naming conventions. It's like how some celebrities go by their stage names instead of their birth names. Section 7. Acid antics. A quick recap and a fun fact. Congratulations, science explorers! You've made it through an exciting journey into the fascinating world of acids. You've journeyed into the world of acids and learned how to name both binary and oxyacids. This knowledge is fundamental in understanding how these substances interact in various chemical reactions. Remember, binary acids are a two-part harmony of hydrogen and another element. These are the simpler acids, but they play a crucial role in many chemical processes. We use the hydro prefix and IC suffix to name them in solution. For example, hydrochloric acid, which is a combination of hydrogen and chlorine, is a common binary acid. Oxyacids, on the other hand, are like musical ensembles with hydrogen, oxygen, and another element. These acids are more complex and are found in many biological and industrial processes. We use the OUS suffix for it-oxyanions and the IC suffix for ate-oxyanions. For instance, sulfurous acid comes from sulfite and sulfuric acid comes from sulfate. And here's a fun fact to impress your friends. Did you know that the pH scale, which measures the acidity or alkalinity of a solution, is actually a logarithmic scale? This means it's not linear but exponential. That means that each whole number change on the pH scale represents a tenfold difference in acidity or alkalinity. For example, a solution with a pH of 3 is 10 times more acidic than one with a pH of 4. This logarithmic nature of the pH scale helps scientists and chemists to easily compare the acidity levels of different solutions. It's a powerful tool in the world of chemistry. So next time you're enjoying a glass of orange juice or using vinegar in your salad dressing, remember the amazing world of acids and their clever naming system. These everyday items are great examples of acids in action. Keep exploring and stay curious. The world of chemistry is vast and full of wonders waiting to be discovered. Whether you're in a lab or just observing the world around you, there's always something new to learn. Make sure to hit that subscribe button. And as always, have a good night.